I'm Sam, so I'm here to talk about Crimson, okay, so there's a surprise to no one in this room, I think, that storage has been getting rapidly faster. Greater IOP density and lower latencies, sort of like every month. But CPU throughput isn't really improving in the same way. We see a pretty nice increase in core counts, but not so much in per core throughput. See a nice little progression here from 20 million cycles per I/O for a hard disk to 300,000 for like a circa 2010 SSD to more like 6,000 cycles per I/O now if you wanted to saturate a single one of these devices with a single core. So those are not super friendly numbers. So if we want to have any realistic hope of saturating these things with any sort of a cost effectiveness, we need nicely, highly parallel to exploit the high core counts and very efficient in terms of clocks per I/O. So Ceph, unfortunately, came about during an age where we could afford quite a few more cycles per I/O. So what do we need to do to adapt Ceph to hit, or to be able to cost effectively exploit devices like this? So we'll start with a quick refresher on the Ceph architecture. So Ceph supports sort of three different access modalities: object, block, and file. So what they all have in common is that they all use the same distributed service called RADOS to actually deal with their I/O recovery, replication, that sort of stuff. So for I/O performance purposes, we're really mostly interested in RADOS, which is comprised of the sort of application client, which would be, for these purposes, the MDS, RGW, daemon itself, the librd layer within a VM, or the sort of Ceph kernel client, right? And then there are two services that exist in the RADOS cluster. There's the monitor cluster, which is a set of typically like 5 or 7 monitors whose only purpose is to produce a sort of monotonically increasing consistent cluster map, which clients and OSDs use to agree on data placement and consistency. But the monitors are not involved in the I/O path. Only the OSDs are involved in the I/O path, as client nodes will talk directly to the relevant OSD, which they figure out by looking at the cluster map and calculating it based on the object name. So for these purposes, the OSD is really where we want to target our efforts if we're looking to improve our IOP per CPU cycle counts. So broadly speaking, there are 3 main components to the OSD I/O pipeline. We have the async messenger, which is responsible for dealing with Ceph's on-wire protocol, which is sort of a mapping of atomic messages onto TCP/IP with all of the relevant restart and message ordering requirements. And then we have the PG here, which reflects the in-memory blob of state the OSD uses to make decisions about op ordering and, for instance, whether an op needs to wait for an object to be recovered, that sort of stuff, or whether a read on a particular object needs to wait for a write to finish before it can continue. Then we have the ObiectStore, which for all practical intents and purposes at the moment means BlueStore. And that includes all of the writing to disk and transactional correctness that we need to actually do I/O. And then finally, the messenger again for replying back to the client. So if we consider a small unreplicated write, and we go sort of thread by thread, a client message needs to be read off the wire by a messenger thread, which then places the message in the op queue. And OSD op thread then picks up the message and creates a transaction, which it queues for BlueStore. BlueStore's sync thread then picks up the transaction, packs it into a RocksDB transaction, passes that off to RocksDB to write to disk. The callback for that is then placed on yet another thread to be picked up by the OSD, and so that a reply message can be created, which then gets put on the outgoing queue for the messenger to send back to the client. And if you're keeping count, that's too many threads, really, for adding up to really quite a staggering amount of just inter-thread communication overhead, even before you get to basic stuff like writing to disk. So even if classic OSD is doing a lot right, there's probably a lot on the table here to be improved. So here's a flame graph I've borrowed from Kifu and Radek's presentation from CephLCon Barcelona last year. And we can see a few of these threads here. On the bottom at the left, we have this FN anonymous, which is actually the callback that the OSD queues for BlueStore to call when the I/O is complete. Notice this is just completing the I/O. It's not like the I/O itself already happened. This is just the callback. The messenger worker there is the async messenger thread that does both sending and receiving, so that's good news, since the footprint there reflects both sides. And then the big part on the right is all of the processing that happens in the OSD itself. That would be the messing with in-memory PG state part. If we zoom in on the callback, we see that we spend quite a lot of time here messing around with mutexes. This would be serialization on the PG lock. This happens because 2 or 3 of those 4 thread groups all touch the PG state to one extent or another. So even if you have pipelined ops on the same PG, you'll still tend to serialize on the PG lock anyway. And if we zoom in further, we see yet more mutexes. I believe that one's actually, since it's in do OSD op effects, that would be the watch notify ball of state, which actually coordinates with the messenger threads. And then as a bonus, we also see that we spend quite a lot of time in the kernel's TCP/IP stack. So with that background, the goal here is to essentially attack this problem by replacing the OSD with something new, because it would be super hard to replace all of these different interacting thread pools with something that doesn't do that, because the reason for those thread pools is that the classic OSD is built on top of blocking I/O. So if we want to do a bunch of things at the same time, we're relying on the kernel to do context switches and swap out those tasks when they need to go to sleep with something else. So Crimson's goals are to minimize CPU overhead per I/O, primarily, by minimizing cross-core communication, by minimizing copies, and by minimizing context switches. And we'd also like to enable emerging storage technologies while we're at it, because if we're rewriting an OSD, it would be a bad idea not to pick up the opportunity to exploit some of these newer technologies that are coming out, particularly zone namespaces and persistent memory.
All the hot shit. Whoa.
Yeah, that's right, all the hot shit. So to help meet these goals, we've chosen to use Seastar, a high-performance modern C++ framework originally created for ScyllaDB, which is intended to be a high-performance Cassandra replacement with kind of similar goals to Crimson's. So Seastar's design uses a single reactor thread per core pinned to that core with, ideally, no context switches or other threads coming in at all. To handle multiple requests concurrently, you use asynchronous I/O, and Seastar internally uses essentially a cooperative user space scheduler to swap among ongoing coroutines. It also supports direct support for DBDK, high-performance user space networking library. So the programming model is based around futures, fortunately, rather than callbacks. On the left, we have an extremely stripped-down bit of the async messenger's code for receiving a request. We have here 3 different blocking calls, one read request, another handle request, which will typically involve I/O if it's a read, and send request for send response for sending the I/O back to the client. On the right side, we have that same code rewritten as a chain of Seastar continuations. It's more verbose, but not nearly as bad as if it were passing explicit callbacks. So one nice component of this model is that it's easy to model the case where an I/O call might or might not block at all. This is particularly important with persistent memory, as for reads, there will be cases where persistent memory reads are similar to DRAM reads. And we're not going to want to schedule another coroutine in those cases. We're just going to want to troop right on. But in the case of, for instance, a cache miss, it's nice to have the flexibility to unschedule and do something else. So this does have that nice property. So how do we restructure the OSD to take advantage of Seastar? If you recall the classic OSD structure, threads are sort of grouped by their corresponding steps in the op processing pipeline that can block. So the first one is the read from the network socket, which blocks until data is available, of course. The next one is blocking for space to be available for the PG lock to be available in the PG processing component. Then we block waiting for I/O to complete in BlueStore, and we block again waiting for I/O to be sent, or for the response to be sent back to the client. But since Seastar uses async I/O, we're going to group all of these stages into the same thread. And we'll just use Seastar's scheduler to switch among the things that can run. So in order to avoid inter-thread synchronization, we want to partition the memory accessed by the OSD such that any particular request only touches memory that thread touches. So we don't want requests in two different threads to touch each other's memory. Fortunately, RADOS makes this pretty easy. If you're familiar with the way RADOS maps requests onto OSDs, it actually maps requests onto PGs first. And it makes no guarantees if you send multiple IOs on different objects. There are no ordering guarantees on those IOs, even if they happen to hit the same OSD. So we can exploit this by saying that each placement group, which is a partition of the object space, gets its own thread. And since we typically have dozens to like 100 PGs per OSD, it's pretty easy to spread out the PGs among the set of threads. There is a little bit of a catch. Clients know which OSDs to send a message to via the OSD map by computing it. But there isn't anything at the moment that would allow a client to figure out which thread or which port. Like if we had 10 of these Seastar threads on a particular OSD, if we really wanted that to work, we would need 10 ports open, one per reactor. But there isn't anything in the protocol yet that would allow us to do that. So we would need to expand the messenger and OSD map machinery to make that possible. Or we could just forward the message to the correct reactor, which we may actually do if it turns out to be easier. But at the moment, what Crimson does, because we want to show some initial sort of, yes, we really can cut down the CPU cost per IOP progress, is we're just running one thread per OSD. In the sort of a short term, we can still saturate a device by running a bunch of OSDs per device, but it's not clear that that's really scalable in the long term, especially as we get into dozens of or hundreds of cores per chip. So we're considering that to be sort of future work for the moment. So the current status is that we've ported the code responsible for peering middle last year into Crimson. So the Crimson OSD is capable of doing the work of agreeing on acting sets, shipping around logs, and going active. And we have basic I/O replications, so you can set up 3 replicas, and they will correctly send I/O to each other. And on the back of those two, we have some extremely basic RBD-based benchmarking. However, we can't actually do the part where we write to disk yet. So not a very good storage system as yet, but progress. The parts we're focusing on right now are getting recovery and backfill working, which would be the shipping around of data after failures. We're adding support for BlueStore, which is not entirely trivial to port, and I'll talk about that in a bit. But it's almost ready to merge, so that should work, at least in a limited sense, soon. And we're also writing a new ObiectStore backend for Crimson that will be native and will hopefully exploit ZNS devices, and I'll talk about that a little bit too. So at the moment where we are, and again, this is with in-memory shims for both classic OSD and for Crimson, so we're not writing to disk here. Performance for latency is pretty much the same as classic OSD, which is not great news. And throughput's pretty much the same, which is not great news. But we use almost no CPU while doing it, which is pretty good news. And this is really the metric we're looking at. We're not that interested, especially before we've implemented Seastore, in increasing actual throughput. What we're interested in doing is demonstrating that we can drive the same amount of throughput with like a quarter of the number of cores. So this is what progress will look like for us. It will look like same or better performance on less CPU. So porting BlueStore to Crimson is not super easy. BlueStore has its own internal threading architecture. It's got a thread for callbacks back into the OSD. It has a thread for interacting with RocksDB. As that, when you submit I/O to RocksDB, that's itself a synchronous call. And RocksDB itself uses blocking I/O internally. So the approach right now is to essentially create a pile of threads that are external to the Seastar framework that we talk to over an asynchronous queue. This washes away some of the benefits of Crimson, but it will allow us to test things like recovery in the meantime. In the longer term, depending on exactly how Seastore turns out, which is it was probably not a good idea, but the new backend is called Seastore on the Seastar framework, so that will be confusing. But anyway, depending on exactly how Seastore pans out, we may still want BlueStore because it does have positive properties for hard disks. LSM trees get a bad rap for CPU cost, but they're pretty good for optimizing for big sequential transfers. So if we do decide we want BlueStore in the long term for Crimson, we have a path to this. Seastar internally has a neat little trick that uses stack swapping to fake synchronous I/O within its reactor threads. Unfortunately, RocksDB has an internal abstraction that some of you may be familiar with, the env abstraction, where you can plug in essentially whatever you want as the file system layer. In fact, BlueStore already uses this to create the simplest possible file system interface that just backs up to BlueStore's internal allocator. And Kifu has done some work to demonstrate that he can run RocksDB on top of Seastar's sort of stack swapping coroutine-based fake thread interface. And that's pretty easy because of the existing env interface. For BlueStore, it'll be a little tougher because BlueStore wasn't written with one of those interfaces in mind, but it's not an unreasonable thing to do and would probably improve the readability of BlueStore in any case. So that is also a thing we are looking into. So while support for BlueStore would be nice, because as I mentioned, for older storage technologies, it could be handy. It's not really appropriate for high-performance devices for a few reasons. One is that RocksDB is really optimized for exploiting big sequential transfers in situations where every seek costs you. But that's not super appropriate for Flash, where small reads aren't really a big deal. Read latency is quite low these days. Moreover, using RocksDB as the BlueStore metadata backend has its own really specific reasons for costing a lot of CPU, namely the encoding and decoding the onode data for the extent location information is shockingly expensive. It takes a significant percentage of BlueStore's overall CPU usage. And RocksDB internally spends a lot of CPU constantly reading and rereading its keys for compaction purposes. So we're targeting Seastore. So Seastore is intended to solve that. One thing that Seastore will choose to do that BlueStore, for instance, does not is we're going to probably have an independent metadata and allocation structures for each reactor so that each of these little PG groups I mentioned before basically doesn't have to interact with each other for accessing storage. That will complicate the on-disk state somewhat, but it should further drive down latencies. So I mentioned before, and we've talked about this quite a lot today, that we are targeting ZNS. And ZNS is intended to expose a fundamental reality of Flash, which is that you can't actually just write to Flash. You have to release the whole erasure block and then rewrite to the pages. For conventional FTL designs, this tends to drive pretty high write amplification, which is not great for normal Flash, but it's going to be particularly bad for QLC Flash. Moreover, for high-performance devices that don't necessarily have a write amplification problem, it tends to drive pretty high write tail latencies for readings and writes. So the interface differences, however, are somewhat maddening for designing a storage system on top of it. The drive is divided into zones. Zones can only be opened, written sequentially, closed, and reserved. Hopefully, this kind of write pattern will be good for conventional SSDs as well, because hopefully it will minimize GC traffic. And if that's true, we may end up exploiting pretty much the same design for both ZNS and FTL, which would be convenient. So before I added some information about the sort of current design direction of Seastore, but I should note this is very current. I'm currently working on a prototype, so this will probably all change. But before I go into that too much, we should talk a little bit about what's weird about the ObiectStore interface under the OSD. The biggest, weirdest thing is that it's transactional. So when you're doing I/O to, or a write to one of these objects, The write might span multiple objects, and you can include a bunch of things in the transaction. You can write to disjoint offsets within the same object or within different objects. You can include clones between objects. And the OSD uses these things to support things like RBD level clones or RBD or RGW level bucket indexes, atomic updates of multiple keys within the same bucket index. So the object store supports the sort of big flat namespace of objects that are keyed by user controllable names. So the names can be somewhat large. They aren't just like integers, which complicates matters somewhat. Particularly for RGW, the object names themselves are derived from the S3 object names, which can be big. Each object contains two big categories. It's got this sort of key value mapping, which is used primarily for RGW bucket indexes. If you need to, the thing that maps for an S3 bucket, the list of objects that exist for that bucket is kept in a set of these objects, and also a data payload, which is less weirdly just like the 4 megabyte chunks of data that comprise RBD objects and CephFS files. It also supports ordered listing of both the OMAP and the object namespaces. So at a high level, the Seastore design looks something like this. Each core gets its own root, and under that, there is an H object to onode mapping, which is the mapping from like the object name to all of the allocation information for that object, and also an LBA tree. This is still up in the air, but so far it seems to be the case that it will be cheaper to maintain an LBA indirection layer, even on top of ZNS, because of the potential size of the keys in the H object tree. That is, when we're doing relocation of chunks, when we're doing cleaning on zones, we don't necessarily want to be causing rewrites in these large key trees. We'd rather do them in just the ones that are keyed by logical offset, since that hopefully will be denser and it'll be easier to cache. The cost, of course, is that we'll do more reads, but for devices with very low read latencies, that may not be a big deal. The other option, of course, would be to use like a Btrfs style backref tree for finding the incoming pointers when we need to relocate a block. And that may be what we end up doing, but we'll see. So I mentioned before that it supports transactions in a sort of an arbitrary sense. So transactions are going to be supported by always writing these large atomic, or these sort of atomic journal records, which will be comprised of a set of deltas, which represent logical changes to a physical address elsewhere on the drive, and new blocks, which are anonymous at this point because we haven't written the record yet. But if you look at the sort of, let's say we're writing new block B, which represents a new page in the onode to, or the H object to onode table. So it's logically addressed from D. So we have to update D with a new logical address for its leaf. But we also need to add a new, or potentially a new node to the LBA tree, pointing at B, giving us its logical offset, and also modify its parent. So those two edges are physically addressed. And at the time that this is written, they'll be written as relative offsets. So the delta E prime and the block A will contain flags on those offsets that indicate that you need to interpret them relative to the location of the record whenever it hits disk. This trick should allow us to avoid this like double write metadata thing where you have to write out the thing and then write out the metadata indicating where it went. For persistent memory, this is a little less formed, but the goal is probably to take metadata structures like the onode tree, or much more likely the LBA tree, since that's an obvious win. And those are both areas where we expect high overwrite rates, and move those kind of modularly into persistent memory and update them there. So that's all I've got. Questions? Somehow I expected this.
Yes, I love your work. So yeah, that's you're going all in. So I wonder what you said with like conventional SSDs and like you do sequential writes for the zones, but you said it could apply to an SSD.
I'm sorry, what's that?
You said like you didn't need CNS, but you can apply it to a conventional SSD. Just of course, we
Much
need
will
this
depend on what the actual difference in GC traffic turns out to be.
Yeah.
But one could imagine that if you really did write like this, maybe it decreases GC traffic by
Yeah.
a significant amount.
Well, so the key is if we do it in parallel. So if there's multiple writes going in,
Yeah.
they all end up in the same bucket within the SSD. Write AM goes through. But if you have one at a time, it works.
No.
Okay.
Is there any way perhaps to force the drive to put different streams into different places?
Yes, streams.
Is it the streams API?
Yeah, but but that depends on how many you want to have open. Like if a stream SSD has maybe less than whatever, not that many streams, and then CNS have whatever, like much more.
Yeah.
So it really depends on the data placement scheme. I know you said RocksDB. I know from Hans's study, we're looking at 30 zones or so that are open at the same time. So that plus this awesome scheme around it, that's kind of where we look at. That's so depending on how many you need for the BlueStore, and then plus RocksDB, which takes like 30, 35 open zones.
Well, for the record, this won't be using RocksDB at all.
Okay, but
The-
whatever,
but,
whatever that implementation
Yeah.
ends up being.
So
Yeah.
the number, and we will definitely have flexibility about how many of these things we want to have open. I said we'd have one metadata root per core, but that may not be strictly right.
Yeah.
It depends on what ratio of cores we need
Yeah.
to do the sort of non-writing to disk part, compared with the number of concurrent streams the disk can support. So it may be something more like you get like 2 OSD threads and 1 Seastore thread.
Okay.
And we can also control the number of streams we use for each one, because we almost certainly want 2, right? We want one that we write the current journal data to, and we want one writing the data we're relocating.
Yeah.
That is long-lived blocks.
Yeah.
So we'll see.
Okay. Cool. I hear you get the trade-offs. Awesome. Good. Awesome.
Maybe.